Welcome to the final gas laws lesson for this unit. We have covered combined gas law. That's what we've seen already. So just so you know, it started off with these three scientists and their group that they came up with, like Charles studied the volume and temperature relationship, the Boyle studied the pressure and volume, and Gay-Lussac studied the pressure and temperature relationships. So from there, their studies were combined all together, and we came up with the combined gas law here. So again, if you were looking at Boyle or Gay-Lussac or Charles laws type problems, you could still use the combined gas law. You just cross off like the information that don't know. So like if temperature is constant, then just cross it off and then just calculate what you have left and so forth. Okay, so the combined gas law works when you have those initial conditions and then final conditions. So you start with a gas at a certain temperature, pressure, volume, whatever it is, and then you end up with that same gas at a different set of conditions where the pressure changes, volume changes, or the temperature changes. Okay, so you're supposed to go through and calculate out what you need. From there, we looked at Avogadro's law. That's where we started to look at the amount of particles that are in the gas, so we went from pressure, temperature, and volume, and we also added the amount into the mix. Okay, so we ended up going to the ideal gas law with a new formula here. So and then we also looked at molar volume. So because we looked at with Avogadro's law that gases that have equal volume will contain the same number of particles or entities. Okay, all right. So then we came up with this, 1 mole of gas at STP, which is 0 degrees Celsius and 101.3 kilopascals. So at those temperature and pressure conditions, so any gas will occupy 22.4 liters of space. Okay, so sometimes you can use this because it's a lot less calculations, but sometimes you'll need to use this if you are dealing with amount and moles and so forth. Okay, so here is another little guideline here. So taking all of the combined gas laws plus Avogadro's law all together, we come forth with the ideal gas law here. So now that we've seen all of these different laws and methods of tackling the gas problems, you are now going to go through today, and I'm going to throw you various examples that you've seen before, but you need to make a decision as to what plan that you're going to use in order to get to the answer. Okay, so that's the new part today. You just have to make a decision with the tools that you've picked up already in this unit, what is the best tool to use in order to solve the problem. All right, and so we're just going to go through these 5 examples here, and just go through and solve it. So just like another day of kind of reviewing everything we've covered, so it's a good way to finish. So to make the video shorter, what I'm going to do is I'm going to set up the given information, the required information, and then we're going to talk about the action plan. And then from there, once we figure out what to do, I'm just going to pause the video and just kind of go through and finish off the question, and then and then show you both ways. So that way the video is shorter, because you should know how to calculate everything out. You've seen all these. It's the problem today is just when I'm throwing you all the different types of gas law questions at you, do you know which method to select? Okay. All right, so here's the first one. We have a small balloon, and we have helium gas in it, and there's a temperature and a pressure that it's at, and we want to know what volume this gas will occupy at 10 degrees and 101 kilopascals. Okay, so let's just write down everything we have here. So we have initial volume here of 275 milliliters. Okay, and then we have temperature of 25 degrees Celsius. And then we have a new temperature 10 degrees Celsius, sorry, and then, sorry, that we have the initial pressure as well. Okay, and then we have our second pressure. Okay, and then it's saying what is the volume of the gas when it's at these new conditions here. Okay, so there we go. So that's the required. All right, so from there, we need to think of our action plan now. So which one of the gas law will we use here? So we're looking at, so we have, initial conditions and final conditions. So if you look up here, there's nothing about mass or amount. So, you'll eliminate these ones here, and then the combined gas law is the way to go. Okay, so that means it's PV over temperature and equals pressure times volume over the temperature as well. Okay, so what's happening here with combined gas law is that, the amount is constant. Okay, we're not changing how much gas we are analyzing here. That's staying the same, just the other conditions are changing. So that's why we're going to use combined gas law, and we're not going to use the molar volume or the ideal gas law where they need you to calculate or have some information about the amount in moles, okay? So here there's nothing about amount in moles. So we're making the assumption that it's constant. Okay, I know it doesn't say here, but it just says it's a balloon, right? So we're going to assume the balloon can't leak any of the gas out. So it's at these initial conditions, but then suddenly the condition change. It becomes these conditions here. So we're going to go through and just figure out the volume from there using the combined gas law. So again, we can rearrange this before we actually start calculating. So we want V2 by itself. So I'm going to move the P over here by dividing it, because right now it's multiply, and then I'm going to move the temperature by multiplying it over because it's divided right now. So what happens here is temperature goes to the top, temperature 2, and then pressure 2 goes to the bottom. Okay, so maybe I should point those arrows the right way here. So I'll just write this in here first. Okay, so yeah, pressure 2 goes there, temperature 1 or temperature 2 goes there. Okay, all right, so there's the equation, and then just a reminder, make sure change your temperature by adding 273.15 to both your degrees Celsius numbers here. And kilopascals is in the right units. Oh, and then volume here, we want it to be in liters. So divide it by 1,000, and then we get to the liters value here. Okay, so I'm just going to stop the video. I'm just going to go through and calculate it, so you go ahead and do that as well. Okay, I realized I put T of 1 for this one. I meant T of 2. This is the second temperature. All right, so we went through and threw our information into the equation here. So this is the one that's a bit tricky to use unit analysis on, so that's why I just use the formula and just rearrange it to where you need to, and then place the values where they need to go. Okay. All right. So, yeah, we just go through, we calculate it out, and we get to 0.90. So again, for people that are calculating things wrong, make sure to multiply everything across the top first, hit equals, then divide, put these in brackets, multiply them together, put them in brackets, closing bracket, equals, and then you should be getting this value here. And then I looked back up at the original numbers here. Everything's got 3 digits, so the answer will have 3. 1, 2, 3. The leading 0 doesn't count, so the final volume is helium is 0.905 liters. Okay, so we're on to example 2. Find the volume that 20 grams of carbon monoxide gas occupies at STP. All right, so let's write down the stuff that we're given here. Okay, so we have a mass of carbon monoxide, so that's CO. We know that it's at STP, okay, and you could write those out if you need to. And again, those are on the back of your formula sheet. Yeah, okay, so and then what we need here is we need the volume. of carbon monoxide. Okay, so we're trying to figure out what method to use here. That's the main part of today's lesson. So if we're going back up to the little table here, so we have a volume to find. We have a mass value. We know that it's at STP, okay? So again, the ideal gas law, it can be at any temperature and pressure, okay? So you could use it to find anything that has, amount, mass in it. But molar volume, if we know that something is at STP, molar volume could be fewer calculations, okay? So it can end up with fewer calculations, so you might want to use this option. But I know some of you like just kind of memorizing one method and just using that method, and that's fine, okay? All right, so we could do this example with both of these, and we'll find that the answer is pretty close, okay? All right, so if we're going to use the molar volume method, that means we're going to somehow use this 22.4 liters equals 1 mole, okay? So we stack them up in some way. If we're going to use the ideal gas law, then this is the formula that is the ideal gas law. And so we have the mass and we need to get to volume, right? So we need to go to volume. So what we're going to do is you're going to go from mass to moles, then to the cloud that you want to go to, okay? So mass to moles, and then if you want to use molar volume, you're going to use this value here. But if you're going from mass to moles, and then you want to use ideal gas law, then you're going to use this equation here, okay? So, so you need to go from mass to moles, so you need to get the formula from a few units ago. So to get to mass to moles, we're going to use this one. Once we have this one, we're going to use ideal gas law to find the volume. So we're just going to rearrange this one to look like that. Okay? So, so I'll show you both ways here, and we'll get to our answer. So we're going to look at the molar volume method first. Okay, so again, we need to get to moles for both of them. So we're going to do that by using this formula here. Okay, so the mass was 20 grams, and we found our molar volume, or molar mass, to be 28.08 grams per mole. And that ends up being 0.714, etc. moles, okay, of carbon monoxide. So that mass of 20 grams is this amount in moles. And then from there, to get to the volume of carbon monoxide, we are going to take that amount, which is in moles, right? And so just, again, carry more digits here. And then we're going to multiply this conversion factor here. So we want to stack these numbers up, but we don't want to put mole and mole together on the same line. So we're going to put mole down here and 22.4 liters here. Okay, so if we're trying to get to liters, put the liters at the top. If you're trying to get to moles, put the moles on top, okay? All right, so then we'll take that number, multiply by 22.4, and you end up with 15.994, etc., okay? And then liters. So if we're looking at the significant digits here, 3 digits, so we need 15. So we need to keep this one, so we need to go to 16 liters like that, okay? So that's 3 digits. All right, so, and then we'll do the ideal gas law. All you're going to do is use this equation here to get to moles, which we did there, and then you're going to use the volume equation in order to get to the volume. Okay, so here's how we can find the answer using the ideal gas law equation. So again, we rearranged it so we were finding volume. So we want to go from mass to moles, then to volume. So we are taking this amount equation and then finding the amount using our mass and our molar mass, and then we're going to calculate using this one here, okay, for the volume. All right, so we did that, so I just grabbed the value from our previous method here, and then we are plugging in our amount, all that stuff, calculating it out, and then we get to 16 liters, okay? So there is the same volume with both methods. And I know the unit analysis people want to see their method. So again, start with mass, go to molar mass next, flip it, okay? Then grab your R value, and then from there you'll know where to put the temperature, where to put the pressure, and then when you cancel everything out, liters will be left standing, which is what we want, and then we get 16 liters that way as well. All right, and then our final statement here is the volume of carbon monoxide when the conditions are STP, standard temperature and pressure. The volume will be 16 liters. Okay, example 3. So we have find the temperature of a 2.5 mole of gas that occupies a volume of 56.5 liters and a pressure of a 121.15 kilopascals. Okay, so let's go through, write all this stuff down. So we have an amount. Okay, so again, you should be able to recognize everything by the units. We have volume and a pressure. Okay, and we need to find the temperature. Okay, so again, we don't have initial and final conditions, so not this one. We don't have STP as our standard temperature and pressure as our conditions, so we have ideal gas law to pick. All right, so here's the plan. PV equals nRT. Okay, and we have N, we have R, it's a constant, we have pressure. So in order to find temperature, we need to rearrange this equation. So R and N will move over here and be divided away. Okay, so there's our plan. Now we're just going to put it into action here. Okay, we're going to start with the formula method first. So we just take our formula that we rearranged, throw everything in where it's supposed to go, and then calculate it out. So again, multiply the top, divide, put everything in the bottom in brackets, multiply them together, equals, and then we need 3 significant digits here, okay? Okay, there's 3 here, 5 there, so 3. And there we go, we'll write it with units. All right, if you want to use the unit analysis method instead, again, start with volume. Remember to start with volume. And then from there, kind of start stacking everything the way that you need to in order to get rid of the units, all right? So we start with volume here, liters, and then so I used R value next, so I knew which way to stack those. So since liters is already at the top, we'll flip the R value, gas constant, to the bottom like that, and then put mole and Kelvin at the top. And then from there, we know which way to stack so we need to get rid of Kelvins. Sorry, we don't need to get rid of Kelvins. We need to get rid of moles, so we put the moles here, and we need to get rid of kilopascals, so that goes to the top. Okay, and liters will disappear as well, so we are canceling out the liters, canceling out kilopascals, the moles, okay, and that leaves just Kelvins left, which is what we want, and we get to that same value, and the temperature of the gas is 331 kelvins. Okay, so we are at standard temperature and pressure, STP. We have a mass of hydrogen gas that reacts with 8 liters of chlorine gas. How many liters of hydrogen chloride gas are produced here? Okay, so right away you're thinking STP, maybe molar volume and so forth, right? So let's just go through and write out everything that we're given in this problem here. Okay, so also on top of it, hopefully you are noticing that there is a reaction happening here as well, okay? So write that reaction equation out. So we have hydrogen gas reacting with chlorine gas. So again, hydrogen is diatomic gas, reacting with chlorine gas, which is diatomic, and it's producing hydrogen chloride gas. Okay, so again, it's not talking about solutions or anything, so you're not writing AQ, but you are writing G for the gas, okay? All right, so then from there, double check that it's balanced. Okay, so 2 hydrogens, we need a 2 here, and then 2 chlorines, 2 chlorines. So we're good now, we're balanced. Okay, and we're gonna write everything we know, so we know the mass of hydrogen. And it reacts with 8 liters of chlorine gas. Okay, how many liters of hydrogen chloride, okay, are produced. Okay, so that's the unknown. Okay, so you have to start thinking about how do we go about solving this one here. Okay, so we need to figure out how we're going to go about attacking this question here. So again, we know that we're at STP. Okay, so that's a clue as well, what gas law that you want to use. But we're going through and we're given we have a reaction, right, happening here. We're given information about both of the reactants, but it's not telling us, you know, that one was in excess. We don't know which one was the limiting reagent. So we don't know which one actually runs out first in order to form this, okay? So remember, the one that runs out first controls how much actual hydrogen chloride product will form, okay? So that's the one we have to figure out, and then we use that to calculate here. So in order to do this, we can kind of calculate both of them at the same time, all the way, you know, start with the mass here and calculate to the volume. Start with the volume here, calculate to the volume, and then whichever volume is lower is the limiting reagent, and then therefore that's the answer, okay? So, so what we're going to do, so if it's hydrogen, so if hydrogen is the LR, okay, so limiting reactant, then what we're going to do is we're going to find the moles. Okay, so we're going to go hydrogen. So right now we have the mass. We're going to go and find the amount of hydrogen. And then we're going to go and find the amount of hydrogen chloride. And then we'll find the volume of hydrogen chloride. Okay, all right. And then if chlorine is the LR, what we're going to do here is see how it's a volume to volume question, right? Volume to volume. So when we're at STP here, remember, so just we learned about Avogadro's law, where if you have you know, the same temperature and pressure, you're going to find that you can just use the mole ratio in order to find the volume of the other one. So if we know the volume of chlorine, we're just going to use the mole ratio to get to the volume of hydrogen chloride. Okay, so let's just jot those down so we'll remember what we're supposed to do. Okay, so we're just going to use the mole ratio, or actually in this case here, we can call it volume ratio, right? But we're still going to use the coefficients here to find the hydrogen chloride volume. All right, if we're going to use this method here, this is the one we've seen a lot. We're going to use molar mass to go from mass to moles. Okay, and then this next step here, we're using mole ratio, using the coefficients from the balanced chemical equation. And then the last step here, again, because we're at STP, I can use molar volume, or I could use the ideal gas law, but I'm going to just use the molar volume here. Okay, so this condition here, we just need to figure out which way it flips. Okay, so let's find them both at the same time and then just calculate right to the end the volume of hydrogen chloride. And the one that's less is going to be the limiting reagent, and that's what the final answer will be. Okay, so let's start with hydrogen here. So if, okay, hydrogen is the limiting reactant. So we're going to start with finding the amount of hydrogen. Okay, and again, we have the molar mass of hydrogen is 2 times 1.01, which is 2.02 grams per mole. Okay, so we're going to take our mass of 0.72 grams, calculate that out. Okay, and then we get our amount. Etc. Okay, keep that number in your calculator. Okay, so that's the amount of hydrogen. So we're going to use the mole ratio now. So hydrogen to hydrogen chloride, the ratio is 1 to 2. So 1 to 2. Okay, so if our amount of hydrogen is that, what's going to happen as we go this way? We double it. So we're going to multiply by 2. And then we'll get 0.7128, 71-ish moles. There you go. And then once we have our amount, we're just going to use our molar volume in order to find the volume of hydrogen chloride. Okay, so we're going to take our amount here, and then we're going to, because we want liters, we're going to multiply with 22.4 liters at the top over 1 mole, like that at the bottom. Moles cancel out. Okay, and then you end up with a volume of 15.9683, etc., like that. Okay, so I'm just going to carry all the digits for now because I want to compare with the other one to see if that's the limiting reagent. Okay, so chlorine here. Okay, all right, so we went through the formula method here and we found that hydrogen was the limiting reagent here. So now we're going to check to see what if chlorine is the limiting reagent. Okay, so we know that we have the volume of chlorine here, and we're going to go right to the mole ratio here of chlorine to hydrogen chloride. So it's a 1:2 ratio. So if I already know that the volume is 8 liters, well, I can use a volume ratio here and see how when we go from 1 to 2, we doubled it. So I'm going to double the 8 liters to 16 liters here. Okay, so we found our volume of hydrogen chloride just by using the volume ratio. Okay, all right, so if we're looking here and comparing them, we're finding that this one's lower. So hydrogen is the limiting reagent. Okay, so we are going to use this one and we're going to ignore this one. I know they're pretty close, so when they round up, but this is the true value here. Okay, so just going to look at the sig figs here. So 2 digits, 2 digits. So when it comes down to it and we have to round it up, it still comes out the same. Okay. Okay, so therefore, okay, the volume of hydrogen chloride is 16 liters. Okay, all right, so just adding a little bit of extra stuff from like the stoichiometry unit where we had to find the limiting reagent, okay, but still kind of going through the steps of using molar volume here to calculate our final answer, okay. The example for using the unit analysis method. So again, I'm starting off with, okay, so if hydrogen is the limiting reagent, then we're going to take the mass of hydrogen and go through, use the molar mass to get to moles, use a mole ratio here, and then use our molar volume conversion here to get to the volume, okay? And then if chlorine is the limiting reagent, then we're going to go through and again use the coefficients, the volume ratio, to get it converted to the volume that we needed. And then when we're comparing them, we're finding that the hydrogen is the limiting reagent here because its lower volume is produced of hydrogen chloride, okay? So yeah, so then therefore the volume of hydrogen chloride is 16 liters. And I know it ended up being the same, but just go through the process of finding the limiting reagent first before you go and state your final answer. Okay, so here's the last example, example 5. So we're going through and we have some oxygen gas and magnesium reacting to form magnesium oxide. Okay, so we need to find the volume of oxygen that is at these certain conditions here, how much will be consumed in order to produce the magnesium that we have here. Okay, so again, we have a gas reaction here, so let's go through and write out the balanced chemical equation. So we have oxygen gas, we'll have magnesium, metal here, and magnesium oxide. So again, magnesium is 2 plus charge, oxygen is a 2 minus charge, so just makes MgO like that, okay? And it's a solid. All right, so from there, we're looking at balancing the equation first. Okay, so we have 1 magnesium, 1 magnesium. We have 2 oxygens, so we got to put 2 here. So then that changes this to 2 as well. So now we have 2 magnesiums, 2 oxygens. We're balanced, okay? All right, so what information do we have? We know that we have a mass of magnesium oxide. So we have 2.43 grams. And we know that we need to find the volume. Okay, so we need to find the volume of oxygen. But we know the pressure, so I'm just going to put it over here, is 94.9 kilopascals for the reaction, and the temperature is 25.0 degrees Celsius, which when I convert it to kelvins, is 298. Okay, all right, so we know the pressure, we know the temperature, we need to find what volume will be consumed. Okay, so I know we have a couple reactants here, and we're not sure which one's the limiting reactant, but in this case here, we don't have enough information here, so just go with, if they're asking for oxygen, just make the assumption that oxygen is the limiting reagent, okay? So we're going to figure out, so we're going to assume that this reaction formed 2.43 grams of magnesium oxide, knowing that magnesium or oxygen was the limiting reagent, okay? So here's our plan. We need to find the volume. So we need to go from the mass of, so if we make our little table here, so we need to go from the mass of magnesium oxide, okay, eventually to the volume of oxygen. So again, so we need to get to the amount, and then we need to find the amount of oxygen, and then we could find the volume of oxygen. Okay, so here's our plan. So to go from mass to moles, to mass to amount island, you need to use molar mass. Okay, so that means we will need the molar mass of magnesium oxide. So we'll just find that right now. So again, 24.31 and 16 altogether. So that's from magnesium, that's from oxygen. And we'll end up with 40.31 grams per mole. Okay, so then from there, so you'll have your moles of magnesium oxide, and then we're going to use our mole ratio. We have our balanced chemical equation here, and then we're going to go from amount to volume, okay, using, so we're not at STP, so we can't use molar volume. So you need to, but we do need, we go from amount to volume, and we don't have the initial and final conditions. We're not going to use combined gas law, so we're going to use the ideal gas law here. Okay, so there's the equation, but we need volume, so we're just going to rearrange this. So it looks like that. Okay, all right, so there's our plan. So let's, just put that into action here, calculate it out, and then check your work. Okay, so I did the formula method first. So we calculated the amount of magnesium oxide first by dividing it by the molar mass. Then we did the mole ratio. Okay, so we're going to go 2 then to 1. So we're going to divide by 2. Then we get the amount of oxygen. All right, and then once we have the amount, we're using ideal gas law, crunching all the numbers in here and getting 0.787 liters. Okay, so that's the formula method for the unit analysis, people. So again, we're starting with the mass. We're using our molar mass to get to the moles island by flipping, okay, the molar mass. Then we're going to use the mole ratio. So again, the oxygens was what we need to find. Okay, so that's the unknown, and then the known goes on the bottom. Then we're going to throw in the R, the gas constant, right away, so we know how to stack everything else up. Okay, And then, so yeah, so kilopascals is at the top, so that means pressure. Kilopascals is at the bottom. Kelvin's at the bottom already of R, so we're going to put the temperature up at the top, so the kelvins cancel out. Okay, so once we cancel everything else out, liters is left, and then we get to our final answer here. Okay, and we make our therefore statement. All right, so now that we've seen these questions again today, you should be pretty confident at selecting the right tool that you need in order to solve the problem. So we're going to have checkpoints here. So I want you to practice the worksheet, get some more, just practice in with selecting the right methods, but also getting to the right answer as well. All right, and then try the checkpoint.